Okay, so this is lecture 11 for sparse matrix. So, our up to lecture 9, we have discussed about the diffusion simulation, a part of process simulation. So we wanted to summarize our diffusion simulation, but not in its physical content, but from the viewpoint of numerical analysis. So now we can solve a set of equations, set of actually differential equations. So what we can do right now is do certain transient simulation. So if we have certain kind of time derivative term, then we can solve it. So introducing by some time derivation. Yes, this is of course an approximation. However, if we accept this kind of approximation, so-called backward Euler, backward Euler approximation, then we can treat this term, the quantity at the previous time instance, as a fixed quantity and treat this quantity as a unknown variable. So when the past values are given, then we can just solve the present value with just conventional steady state simulation technique. That was one thing we have studied in our previous lectures. And boundary condition. So maybe you remember we have drawn the concentration as a function of position, and at this boundary, what was the applied bias? There was Neumann boundary condition. Actually, it's a homogeneous version. Homogeneous version means that there is no flux of our dopant flux. So now this is homogeneous Neumann boundary condition. And what was the boundary condition applied at this point? So the value was just fixed. There was no change, and fixed boundary condition was applied, and it was Dirichlet boundary condition. Although we have not explicitly applied the Dirichlet boundary condition, but anyway, for right boundary there was Dirichlet boundary condition. So now we can consider two different types of boundary conditions. That was not that difficult. And you remember that we have already discussed multiple unknown variables. What was it? One was boron concentration and one was arsenic concentration. So then how can we assign these two different quantities into one single vector for unknown variables? Of course, there can be many different ways, but preferred way is position-wise assignment. So when we have a long vector for our unknown variables, then usually we wanted to assign something like this for certain x and some certain x. We assign different values and they are assigned nearby. After that, we introduce another set, CBXI plus 1, also CASXI plus 1. This kind of position-wise assignment was recommended. And another one was non-linearity. So when we just consider simple diffusion, then yes, this was a linear system. However, when we consider drift term into our equation, then the system becomes really non-linear. So maybe you remember that we have spent some time to study Newton-Raphson method to solve complicated nonlinear system. So once you have done our homework successfully, then now you can solve the nonlinear system without much difficulty. So I think that actually through this process simulation, we have already studied many required numerical technique to tackle both of process simulation and device simulation. Usually in our previous lectures in the previous semesters, we spent quite a lot of time to study these things together with the device simulation. But in this semester, with the process simulation part, we have already covered many numerical techniques already. So I hope that we can much faster go in the device simulation part. So before diving into our device simulation part, I just wanted to say this one. After spending several lecture hours on process simulation, we have found that essentially the numerical simulation or solution of a set of differential equation is reduced to actually the solution of calculating the solution of ax equal to b. Here a is a matrix, x is an unknown vector, and b is a given vector. So what is x? That is our ultimate goal. So if we can do it quickly, then we can get the final solution quickly. If it takes too long time, prohibitively long time to calculate x, then actually, practically, we cannot solve that problem. So our natural question is then how can we make the efficient code to solve ax equal to b when b is given and a is given. You know, today we assume that a is a given vector. We cannot change it. And also b is also given vector, so we cannot change it. We will assume that they are given. So under the given condition of a problem specification, we wanted to talk about how can we efficiently calculate this solution vector x. So let's go to this one. So our answer to this desire to speed up our solution is the use of extensive use of a Stubbs matrix. So let's go to this way. So let's consider a simple example of a matrix equation ax equal to b. So let's come back to around lecture 3 maybe. So at the starting point of our discussion, we have introduced steady state diffusion equation. So steady state diffusion equation simply means that we have no terms related with this kind of thing. So now then we have just second derivative of concentration with respect to the position variable x, and that should be 0. That was our steady state diffusion equation. Then of course when we have such kind of equation, the natural step, the next step is now discretization of this second derivative, and we know it. How can we do that? So that was not that difficult. xi plus 1 minus 2 xi. For this simple case, we can plus x minus 1 and divided by squared delta of x. That was simple approximation to discretize this second order derivative. Of course, this delta x squared can be eliminated from left hand side and right hand side, and eventually we have a matrix corresponding to this second order derivative. So actually that is just related to this non-boundary laws. So this law just shows that the second derivative evaluated at x equal to x1 equal to 0. And this third line says that same quantity evaluated at x2 equal to 0. So now we are collecting the steady state diffusion equation evaluated at x1, x2, x3, and x4. For other points, other 2 points, say x0 and x5, two boundary conditions, we just apply certain boundary conditions. So when we read this law, and when we read this law, we can immediately calculate that C of x not equal to 0. So can you follow me? So just evaluate this matrix vector multiplication, then we have just C x naught, and that is equal to 0. And if we evaluate it in this way, then we find that C at x5 equal to 1. So that is the case. So simply we just apply the left boundary. Oh, I made mistakes here. Left boundary, we have C0 equal to 0 and C at the right boundary equal to 1. We have applied this one. The AX equal to B equation shown here is of course corresponding to a small number n equal to 6. Yes, that is easy to visualize, but you can easily make it prohibitively large. So for example, if you say n equal to 100 or 1000, million, billion, then of course the physics itself is quite simple, but you can make it very, very large. Okay, so are you with me? So with 10 to the 6 as the value of n, then you will have 1 million by 1 million matrix A, and or 1 million entries are in our vector C. Yes. So it is easy to make it large. So then let's think about the number of non-zero entries in this matrix A. So how many non-zero entries are there? Then you can see that there are n rows. So among them, we must neglect the first one and the last one because they are assigned to unknown boundary conditions. So we have just n minus 2 rows assigned to this kind of description. So when you come back, then how many for each row, how many non-zero elements are there? You can find that 1, 2, 3. For third one, 1, 2, 3. You can easily understand for each row you have only three non-zero entries. So simply speaking, in each row you have three entries. So total number of non-zero elements for these rows just given by 3 times n minus 2. And finally, you have two boundary rows, and for two boundary rows, you have just 1 and 2 non-zero entries. So that's it. When you make a sum of them, then you will find the sum becomes just 3n minus 4. If you remember, the size of A matrix is n by n, then in principle we can have n square entries inside this matrix. However, in reality, we have only 3n times minus 4, 3n minus 4 non-zero entries. So if we calculate the ratio between them, 3n minus 4 divided by n squared, if we have a very large n value, not 1, 2, 3, but million, billion, in that case, actually this number 4 doesn't play any role, so we can safely neglect it. So we will have a ratio corresponding to 3 over n. This is the ratio between non-zero elements and the total elements. If we have a very small ratio, it means that simply this matrix is almost empty. Almost all of them are just number 0. So we define a quantity called sparsity of a matrix. The number of zero-valued elements divided by the total number of elements. We have calculated the ratio of non-zero elements divided by the total number of elements. So this is actually the opposite thing. So this upper part is non-zero one, and here we have zero valued one. So now we have 1 minus our ratio. So simply it becomes 1 minus 3 over n. So let's try to calculate it. If we have 100 elements, then what is the sparsity? The sparsity becomes 97%. And if we have 1000 elements, of course this is an approximate expression, but please, number 4 is not that important in this case still. So in this case we have 99.7%. You can easily understand, if we have a large number, this number really approaches to 100%. So almost completely empty matrix. Okay, so from these kind of observation, we can find that description of A as a dense matrix. Dense matrix means that in general their entries or elements are not non-zero in general, in many cases, but that becomes quite inefficient because in many cases, for example, think about this one, when we try to describe this A matrix as a dense matrix, then we have just wasting 97% of our resources. So for a given certain number, 8, 3, 4, we wanted to specify it. Maybe this is 1, but we actually it becomes 0. Now we are wasting one double precision number. Then next question, 3, 5. Is it 1? Yes. We wanted to say that 0. We want to say that is this non-zero? No, this is also 0. Of course, sorry about my 3, 4. Of course, 3, 4, in this case, that is non-zero. But let's say 3, 10. Is this 0? Yes, that is 0. 11? 0, 0, 0. We will just specifying double precision 0 to specify this almost empty matrix. So this is quite inefficient. So now you have homework number 10. Oh, why that is 10? Because lecture 10 was done in online. So now, although we are in lecture 11, the homework number is just 10. Your first homework problem is just to solve the Laplace equation. So what is it? Just to solve this equation with different number. You have already done it, so you can just reuse your previous implementation with different boundary values. Please note that we have 0 and 1 for left boundary and right boundary. So please. Then in this case, the solution is quite trivial. You will have just a simple one. So nothing but your c value as a function of x should be x over L. So that is not that difficult. But point is just to solve it with your previous implementation, assuming a dense matrix A. Then draw the elapsed time as a function of n. Then what you will get is like this. Here you have a number and here your time. Then what will happen? You can easily understand there will be certain graphs ever increasing. So when you have 100, 1000, well, so please try to measure it. But I have one caution on this measuring the elapsed time. So maybe it is not a good idea to just check your elapsed time, your watch. So it is not a good idea. Please try to make a certain routine to measure your elapsed time. So are you with me? So also when you talk about the elapsed time, it would be better to consider the time spent for AX equal to B. For example, if you have very large n values, for example million, then what will happen? In order to construct your matrix A, then you will spend quite a lot of time. So don't measure the time spent for constructing A and B. Just to concentrate on this AX equal to B. And in this case, millisecond or microsecond doesn't make sense in our measurement. So please try to increase your n value sufficiently. Therefore, your measured value becomes just orders of second or minute. Okay, so not hours. So in many cases, if that becomes hours, then something wrong will happen. So please try to increase your n value. I'm not quite sure, depending on your system configuration, sometimes you will see the prohibitively long calculation time or insufficient memory problem. For example, if you introduce, for example, n equal to a billion, then what will happen? The required number of your memory becomes 10 to the 18. So do you have such kind of huge memory in your system? So maybe not. So you will have some difficulty before constructing your A matrix. Okay, so please, anyway, please try to do this one. Then you will find that actually it's not that easy to make a huge system out of your current implementation. So I think that more or less you are working on several hundred points or several thousand points. That was the reason why you were able to calculate our homework problems. But if we go to much larger number, then certainly we will have many practical problems. So the homework number 1 is assigned to understand our current weakness. So our current scheme is not suitable for large system like several 10,000 or larger numbers. Okay, and let's go to now sparse matrix. So for a dense matrix description, how many double precision numbers are needed for store your non-zero values? We need square n entries. Okay, so that is quite easy to understand. However, for a sparse matrix, how many double precision numbers are needed? In this case, we have to memorize only non-zero values. For example, let's just think about this one. We have 1, 1, 2 matrix. This is 3 by 3 matrix, and actually this one becomes 1.0, 1.0, and 2.0. Then essentially, if we memorize 1.0, 1.0, and 2.0, then it is enough to specify this matrix. This matrix in general, we had to memorize 9 numbers, 9 double precision numbers, but in this case we are quite safe to remember only 3 numbers. Of course, your natural question is, from this 1.0, 1.0, and 2.0, how can we reconstruct this original matrix? That is a natural question. For example, if we have this 1.0, 1.0, 2.0, then possible calculation is, for example, this one can be one possible realization of this matrix. Or sometimes you can say that 1.2, 1.2.0. Of course, this matrix also have non-zero element shown here. So now you can understand, in a sparse matrix, it is not sufficient to memorize only non-zero elements. In addition to these unknown oh sorry, non-zero values, non-zero elements, we have to specify where are they. So for example, let's say that 0, 0 and 1, 1 and 2, 2. Let's assume that we have augmented these coordinates to our double precision number. Then what will happen? Then we can uniquely define a matrix A as 1.0 and 1.0 and 2.0. So are you with me? So if we have a certain any matrix A, then following certain rule like specifying its coordinate and its non-zero value, specifying the coordinate and its non-zero value, specifying coordinate and its non-zero value. That is sufficient to uniquely define this matrix. So are you with me? So of course, just to specifying the double precision number for non-zero elements, it is not sufficient. We must specify a pair of row and column. Yes, we have several of them. Then, for example, we may need 2n, oh sorry about that, once again, 2, not 2n, 2 times n and z non-zero integer numbers. So now let's try to make a simple, let's make a really a simple evaluation. I will give you a simple 1, 2, 1, minus 2, 1, and 1. All other entries are 0. Then please specify this matrix A with our sparse matrix representation. Then how can you do that? Then you would like 0, 0 and 1, 1, 0, 1, 1, 1, minus 2, and 1, 2, 1, finally 2, 2 equal to 1. So you will have this kind of description. Then please try to count what is the storage you have spent for this matrix. So you have spent 5 double precision numbers. Okay, then you have spent 10 integer numbers. So are you with me? Then let's try to specify this A matrix with a dense matrix representation. Then we will just say that 1.0, 0, 0, 1, minus 2, 1, 0, 0, 1. How many double precision numbers are needed? Then we have just 9 double precision numbers. Which one is more efficient in this case? In this case, so if we assume that this integer and double precision takes the same amount of storage, then certainly even the dense matrix representation is more efficient. So what happens? It is only because this system is quite much dense. If we have, instead of that, if we have just simple matrix shown here, only one non-zero value, then what will happen? Then we will have just this value for it. So we will have just one double precision number spent for representing it, and two integer number to representing it. However, in the case of a dense description, we still have 9 double precision number starting from 1 0, and all others are just 0. Here we have 0 0 0 0. Okay, so whether sparse matrix representation is more efficient than the dense matrix description really depends on the sparsity. If sparsity is high, then of course sparse matrix representation becomes a good way. In our cases, it is almost always sparse matrix description is a good way to do it. Okay, so please understand, sparse matrix is not always the best one, but in our cases, it is almost always good choice. So good. So now we can understand integer number is 2 times 2 times number of non-zero element, and double precision we have a number of non-zero elements. This is the simplest one we can imagine, but in reality this is not sufficient. So we can have even more efficient description for this one. Of course, it is not that easy to us to reduce this number, because this is already contains the essential part. So we can have here, we can reduce it further. Okay. So we can reduce the storage even further, but we will not talk about this one. Instead of talking about many different tricks to reduce our storage, instead of that, I will just give one example of a well-known format called CSR, compressed sparse raw format. So this example was taken from Wikipedia, so you can visit that Wikipedia article and see. But please have a look at this description. What is it from this one? Now we have 1, 2, 3, 4, 5, 6, 7, 8. What is this number 8 means? Our number of non-zero elements is just 8. We have 8 different numbers, and here we have 0, 0. We have row index, and here we have column index. Then out of them, I will try to make it. So once this kind of description is given, then how can we construct our row? So starting from, its rule is quite simple. Starting from this row, then we are here. Okay, we start from the zeroth row, and we can find that there is column index 0 and 1, and the next row start number 2. So now we can find that between this number starting from 0 and 2, we will have 0, 1. Are you with me? So starting from 0, and before reaching the next number number 2, then we have 0 and 1, and this 0 and 1 number is assigned to the first row. So simply speaking, we will have 10 and 20 for the first row, and this is 0th column and first column. Then let's go to the next row. So in the next row, we start from 2. And before reaching number 4, we have to stop. And 2, 3. And 2, 3 are column index. Now we have 1, 3. It means that 30 and 40 are assigned to the first column and third column. Then let's go to the third row. Third row, here we have starting from number 4, 4, 5, 6. Then what happens? 4, 5, 6, 2, 3, 4. Then 2, 3, 4 simply means that now we have 2, 3, 4. And this is second, third, fourth. Okay, so finally we have 8. So starting from here we have, sorry about that, here we have now 7, and now starting from 7 we stop before 8, so only number 7. And what is number 7? That is 5, and 5 is assigned to 80, so we have 80 and number 5. That's it. The final number 8 is just neglected because that should be the number of all non-zero value. So that becomes our matrix A. So maybe you can feel that is quite weird, because in order to reconstruct a matrix we have to do quite much complicated operation, but you can find that how many storage was spent in this case. The number of non-zero elements is 8, and of course we are spending 8 double precision numbers. And if we do it with our specification like row and column pairs, then we must spend 16 integer numbers to specify this number. But how many were spent in this case? So now you can understand, in the case of a column vector, column index, it is always equal to the number of non-zero, n and g. 1, 2, 3, 4, 5, 6, 7, 8. However, now you can see that there is 1, 2, 3, 4, 5. What is it? This is corresponding to our n value plus 1. So, simply speaking, now it can have, instead of 16 integer values, now we are spending only 13 integer values. Okay, so are you with me? So that is good thing. So of course to you, starting from 16, now it becomes 13. Reduction is not that high, but this is just a small example. If we have a very huge matrix, then of course the reduction will be quite large. So simply speaking, now number of integer numbers spent for that was reduced from 2 times ng. Now it becomes ng plus n plus 1. So for large matrix, always this, in many cases, n and g is much larger than n. How large is it? Even in our one-dimensional Laplace equation case, maybe this n and g is about 3 times larger than ng. So now saving is to considerable number. Starting from NNG, reduced it to NG is quite much. Okay. So of course, I will think that to most of you, the reduction seems to be just marginal, but it's not, and this is quite much important to consider really a huge matrix. Okay, so there are many different ways to specify this kind of thing, but please note that there is one thing we have to keep in mind. This compressed sparse row format is quite much efficient. However, it has one big disadvantage, weakness. Please keep in mind that this kind of thing is quite efficient. However, there is one thing we have to keep in mind. Let's say that we have already made it. So here we have a matrix, and it seems that 10, 20, what was it? I don't remember any longer. 30 and 40 and 35, 50, 60, 70, and finally we have 80. So am I right? So that was it. Okay, from a matrix we were able to successfully build the CSR format for this matrix A. But unfortunately, I have to modify this matrix A. So I wanted to introduce number 90 here. Then what happens? If I have to introduce number 90 here, then I have to first of all introduce 90, 80 here. Then row index is also changed from number 9, and also this number should be changed from this just 5. We must have 0 and 5. Okay, so are you with me? Okay, good. Anyhow, we were able to do that. But instead of that, if we introduce 90 here, then what will happen? Then we have to change all of them. So this one should be 3, 5, 8, 9. Everything should be changed accordingly. So simply speaking, this compressed sparse row format or similar things are very efficient in a memory storage point of view. However, it is very difficult to change it. Then let's come back our more naive description. If we just describe it with this coordinate and number format, then what happens? Then we can just 0, 0, 10, 0, 1, 20, blah blah blah, and eventually we will have 1, 2, 3, 1, 2, 3, and 5 equal to 80. Let's say that we have already made this kind of A matrix. Then if we have to introduce another one, then what we have to do is 0, 2, 80. When we just attach it to the end of this description, then now we have another description for matrix A. Okay, are you with me? So then we can easily modify this A matrix. So everybody happy, but finally, really finally, I wanted to point out this one. Instead of just adding a component, we can consider another cases like this. We wanted to modify a value of a pre-existing element. I wanted to change the value of 0,1. Previously it was 20, but I wanted to change it to 90. Then it means that now our matrix inside the matrix A, we should search it, find out all pre-existing values. Then how can you do that? So if we have this kind of data structure, then we have to first find out whether that the component like 0,1 is existing or not. Is this 0,1? No. Then let's go to the next one. Is this 0,1? Yes. If we find it, then let's just change it to 90. And if we don't find it, then eventually we can add another one or append another one to there to modify the matrix A. Okay, so from this discussion, you can find that sparse matrix in many cases, from the viewpoint of memory management, it is quite much efficient, but at the same time, we have to develop a new format and algorithms and data structure to support them. So that is one. However, don't worry, we are living in the modern ages, so this kind of a complicated job has been done by our ancestors. So now we can just use predefined uh, data structure and algorithms. So up to now, I have spent time for storage description, but more importantly, in my opinion, it is related with solver itself. I mean that the ultimate goal is solving AX equal to B cases. So although there exists a special way, very memory efficient way to store this matrix A, if the time spent for calculating this one is not reduced, then it's not that much attractive. But fortunately, when you have AX equal to B and when A matrix is sparse, then we can find much faster matrix solver for the same problem. Okay, so that is our main motivation to adopt this sparse matrix representation. There are two different types of matrix solvers. One of them is called as direct solvers, and one of them are called as iterative solvers. So direct solvers and iterative solvers are quite much different in its operational case, but if we are lucky, then both of them are quite much reliable. So in many cases, you can just believe there, or you can just trust the calculated result, because you know which one is more reliable. I would say that of course this direct solver is really based on decomposition technique, so this one is more reliable. However, nowadays we have very good iterative solvers, and when iterative solvers says that I have solved that AX equal to B problem, then we can trust it. Okay, so simply speaking, these direct solvers are based on composition technique, and iterative solvers are related with Kirchhoff subspace approaches. So, iterative solvers actually do not calculate the exact solution. So, direct solvers are able to calculate the really exact solution within numerical error, round of error. However, iterative solvers do not calculate the exact one. But you know that, please think about our Newton-Raphson method. In Newton-Raphson method, do we calculate the real solution for our nonlinear system? Actually, not. We just try to calculate the solution quite much close to the real solution. Quite similarly, even when we consider AX equal to B system, we are not required to the exact solution. So if our solution X is quite close to the real exact solution X, then maybe within certain numerical error bound, then we will say that it's okay, we will stop here. So that's the reason why we have iterative solvers. So simply speaking, if your matrix is just moderate, your n is not that huge, then it is better to use this direct solver. And if your n value becomes really large, I mean that from my own experience, there is a certain boundary like this. So if this value is, for example, orders of 10 to the 5, several hundred thousand, or even just a small million, then it works. At least it can calculate the solution. However, beyond that, it is not possible to calculate the solution out of it. So if we have several million or even 100 billion cases, then 100 million cases or billion cases, then there is no way to calculate our solution from direct solvers. Then we have to switch to iterative solvers. And here we have two different representative algorithms. And you know, this one is for a special matrix, symmetric matrices, and this one is for general matrices. However, of course, for special cases, this one works better because more efficiently works, and for general one, this is robust, but it takes more computational burden. Okay. So then, what is the realistic case? If this is not a university lecture course, but if this is just a team meeting for commercial product, then what should we do? Then in reality, many commercial tools are providing both of them. So user should be able to select one of them to have their own freedom to select the appropriate matrix solvers. Okay, so then now let's come back to our lecture itself. Then now anyhow you have to do your homework. Then if you are a MATLAB user, then what should you do is just to change the declaration of your matrix A. Previously, you start from something like this. So starting from this specification, the MATLAB make a certain storage for m by n matrix. And simply speaking, n square double precision numbers are assigned for this matrix A. But instead of that, let's start from this kind of this declaration. Then when you say sparse, then MATLAB do not prepare this kind of huge storage. Then it just say that okay, a matrix is sparse and eventually I will add some numbers. So at the first time this is just a tiny one, and when you add more and more, then it will increase and increase. So since MATLAB is quite user-friendly, so you may not modify any other lines, because in the MATLAB, whether that is sparse or that is dense, that is treated internally. So user just treated them as matrices. Whether A is sparse or A is dense, that doesn't alter the grammar or the routine we have to call. So for example, if I remember correctly, x equal a backslash b. That is the grammar for solving ax equal to b in MATLAB, and whether a is dense or a is sparse does not change this backslash grammar, so you can just use it. Okay, so it is quite easy. And if we go to Python, in the case of Python, you have to be more careful, because they do not they do not support sparse matrix from its own built-in capability. So for that purpose, you have to install SciPy package, and here inside it you have sparse routine, and this is sparse routine, so you can build a matrix with its LIL matrix format. What is the LIN? List in list. So what is it? It's like the format discussed in this part. So it is easy to search and increase. However, this LIL matrix type is not the most efficient one. So simply speaking, it's not CSR. It is less efficient than CSR type, but easy to change its elements. So for that purpose, we start from LIL matrix, and you can just specify their entries. After that, now we have to call our sparse matrix solver. This is sparse matrix solver. However, unfortunately, our sparse matrix solver do not accept this kind of LIL matrix type. So we have to change its format. Fortunately, it has its own method to CSR. So simply calling it, so from a LIL matrix A, we can generate a CSR matrix, and that is self-assigned to A once again. Then using this A, you can use this sparse matrix solver. So seems to be a little bit more difficult, but anyway, this is the code, real working code for our example. So what you can do, if you are a Python user, then you can just type it and increase the number n. Then you will find that you can have a different performance for your Python. And please note that it does not count the time, so of course you have to add more routine to measure the time spent for your matrix solve line. Yes, please try to measure uh, performing this uh, AX equal to B line. Okay, in the case of C++ users, okay, yes, this is just a repetition of our direct solver and iterative solvers, and there are too many ways, and I cannot say that one way is the best and the other one is worse than the other one. So if you are a C++ user, then please do it your way. Okay, which one is better? So I don't care about that. So anyhow, please do your own implementation since you have too many ways, too many freedom. Oh, so now this is lecture 10, homework number 10 for lecture 11. Then please repeat our homework problem once again. However, now you have the sparse matrix implementation, and please draw the elapsed time as a function of matrix size n. You will find that huge improvement in the time for calculating your problem. So then please do not restrict your n values to that of problem number 1. Since your n value, since your program now runs much faster, so for same metrics, your value will be much uh, your your program can be solved much faster. So increase your n values even further to measure the second level was orders of a few seconds or orders of several minutes. So how much you can increase it? So please try to increase your M value as much as possible inside your. So this kind of exercise, they are needed to expand our current work to multi-dimensional cases. So think about our realistic system. Our realistic system is not that one-dimensional. Our system should be two-dimensional or even three-dimensional. In that case, the typical number for n is no longer like 100 or 1000. Simply speaking, let's consider a cube. And now you introduce 100 points along x direction and 100 points for y direction and another 100 points for z direction. Then what happens? Inside this small cube, then you will have 1 billion mesh points inside it. So the number of n corresponding to 1 billion is sometimes seems to be sufficiently large, but in many cases it's not that much. So nowadays 1 million is just a matter of our every daily life. So you should be careful about the efficient way to calculate AX equal to B system. So we are now preparing the extension of dimensionality. We are still confined to 1D, but once you get this capability, sparse matrix implementation, then we can expand our program. Oh, what happened? Sorry about that. I have no idea. Okay, so now we can expand our capability to multi-dimensional cases. Okay, then do you have any question on our homework or lecture contents? Anything? So if you have any question, please let me know. And if you don't, then let's wrap up today's lecture. Thank you for your attention.